welcome to the Explainer. Today we're tackling one of the biggest, most profound questions in all of science. How did life begin? I mean, really, how did our planet go from just a lump of rock and chemicals to being filled with, well, us, with living, breathing organisms?
So, to get started, let's just ground ourselves with this pretty wild fact. It's true. You and a banana share about 60% of the same DNA. Now, this isn't just some fun trivia. It's a huge clue that connects you to pretty much every living thing on Earth, proving we all go way, way back to a common ancestor.
You see, all life today, from the tiniest microbe to the biggest whale, can be traced back to this one single-celled organism we've nicknamed LUCA, the last universal common ancestor. But here's the catch. LUCA wasn't the first life. Nope. It was just the one that happened to survive and pass its genes on. Which of course raises an even deeper question.
Right? This is the ultimate cold case. How did chemistry, the lifeless dance of molecules, suddenly spark into biology? It's a jump that sounds almost impossible, but as we're about to see, scientists have actually uncovered some incredible clues.
So, here's how we're going to crack this case. We'll start with our ultimate ancestor. Then we'll figure out what life even is. We'll hunt for its ingredients in outer space, see how they got cooked up on early Earth, check out the first living bubbles, and finally, discover the revolutionary merger that changed absolutely everything.
Okay, let's dive right in. The ultimate ancestor. This whole idea of LUCA is our starting point. Think of it as the genetic patient zero from which all known life has spread. Understanding it really helps us frame the entire mystery.
But hold on. Before we can find the origin of life, we kind of have to agree on what we're looking for. I mean, what's the real difference between a rock and a robin? For a very long time, that answer wasn't clear at all.
For centuries, a lot of people thought living things had some kind of magical life force. But then, a series of brilliant experiments, like the ones you see here, completely dismantled that idea. First, Lavoisier showed that a guinea pig breathing was really just a form of chemical combustion. And then, Friedrich Wöhler made urea, an organic compound, from totally inorganic chemicals in a lab. The message was loud and clear. Life isn't magic, it's just very, very complex chemistry.
So, scientists have basically settled on a kind of checklist for what counts as life. To be considered alive, a thing has to tick 4 key boxes. It needs to have complex organization, it needs a boundary separating it from the world, it has to be able to replicate itself, and it needs a metabolism to process energy. We're going to use these 4 rules to piece together the solution to our big mystery.
Let's start putting these pieces together with that first rule, complexity. Where do the raw materials, all the complex molecules needed to build life, even come from? Well, the answer, believe it or not, might not be from Earth at all.
This is what's known as the panspermia theory. Now, this doesn't mean little green aliens landed here. It suggests that the basic, non-living ingredients for life were actually forged out in the cosmos and then delivered to a young Earth during a time when it was just getting hammered by comets and meteors.
And you know what? This isn't just some wild guess. We have real, compelling evidence. Using spectroscopy, we've spotted complex organic molecules in distant gas clouds. The famous Murchison meteorite? It was jam-packed with amino acids, the building blocks of proteins. We've even found molecules with a specific handedness, a unique signature of life's chemistry, just floating out there in the void.
So the main takeaway here is this. Space isn't empty. Not at all. It's a huge chemical factory that basically stocked early Earth with all the spare parts it was ever going to need to build its very first living thing.
All right, so the ingredients have been delivered. Now, how did they get cooked? For that, the action moves to Earth, specifically to what Darwin famously called a warm little pond. And this is where we're going to tackle our second rule, replication. Back in 1953, 2 scientists, Miller and Urey, decided to test this whole warm little pond idea. They recreated the conditions of early Earth right there in a flask, the right gases, some water, and sparks of electricity to act like lightning. And what happened? In just a few weeks, the water turned this murky brown, and when they checked it, they found amino acids. They had made some of life's most crucial building blocks from scratch.
But look, making spare parts is one thing. Making something that can copy itself, that's a whole other level. This is where the RNA world hypothesis comes in. The idea is that before the super stable, complex DNA that we have today, life probably used a simpler molecule, RNA. What's so special about RNA is that it can do 2 jobs at once. It can store genetic info like DNA, and it can act like an enzyme to build stuff, including copies of itself. It was the perfect starter molecule for life.
Okay, so now we've got replicating molecules.
But they were just floating around in this chemical soup. To really become life, they needed a home. And that brings us to our last two rules: creating a boundary and finding energy for metabolism.
The solution here is surprisingly simple. Certain molecules, called fatty acids, do something really cool in water. One end loves water and the other end hates it. So what do? They automatically arrange themselves into tiny spheres or bubbles, trapping whatever's nearby inside them. These little protocells were the very first cell membranes, creating a boundary between the important replicating chemistry inside and the chaotic world outside.
But these brand new protocells needed fuel. You know, replicating and building things takes energy. The leading theory today is that they got this energy from deep-sea hydrothermal vents. These things spew out superheated, mineral-rich water, creating a constant flow of chemical energy. It was the perfect environment to power the metabolism of the first, fragile little forms of life.
So there we have it, a bubble, with replicating RNA inside, powered by deep-sea vents. That is life, in its most basic form. But for 2 billion years, that's all there was. The leap to complex life, to animals, plants, and us, well, that required one more incredible event, a 1 in a billion chance encounter.
So first, let's get the two teams straight that were dominating early Earth. For billions of years, life was only made up of prokaryotes. These are very simple, small cells like bacteria. All complex life, everything you can see with your own eyes, including us, we're all eukaryotes. And we came much, much later. The difference between them is massive, and it all boils down to a tiny powerhouse that eukaryotes have inside them.
So the story goes something like this. About 2 billion years ago, a larger, simpler cell, probably an archaea, tried to eat a smaller one, a bacteria. But for some reason, the predator just failed to digest its prey. The smaller cell survived, and it started living inside its would-be attacker. This wasn't an invasion. It was the beginning of the single most important partnership in the history of life. And we are absolutely certain this happened, because the evidence is still inside you, right now. That engulfed bacterium evolved into what we now call mitochondria, the tiny engines that power our cells. And get this, mitochondria still have their own separate DNA. This DNA is totally different from your own, but it's almost identical to that of a modern free-living bacteria. It's a living fossil, a genetic ghost of that ancient merger.
And the payoff for this new partnership, it was a complete game changer. The mitochondria became these dedicated energy factories, providing their host cell with an absolutely astronomical amount of power. We're talking up to 200,000 times more than a simple bacterium could generate on its own.
With this sudden massive surplus of energy, cells could finally afford to get bigger, more complex, and build things they never could before, like a protected nucleus and other specialized parts. And eventually, they could band together to form the first multicellular organisms. It took 2 billion years for life to take that one critical step, but once it did, the evolutionary path to animals, plants, and us was finally open for business.
When you think about it, the chain of events is just unbelievable. From atoms forged in distant stars, delivered to Earth by comets, cooked in volcanic ponds, and then supercharged by an ancient accidental partnership, it's just incredible. It means we really are a product of cosmic chemistry and earthly history. And that leaves you with one last thrilling question. With all those spare parts still out there in the universe's warehouse, what else might be being built right now?